Now, because permutations are so important in probability, we'll spend some time going over a series of examples to, again, just really drive these points home. So the first example that we'll look at is how many permutations exist for a string consisting of 5 letters A, B, C, D, and E. So using our formula from below, that the number of permutations for a set of n elements is just equal to n factorial, we can say that this is equal to 5 times 4 times 3 times 2 times 1, which when you plug that into either your brain or a calculator to factor out, you'll find that that is equal to 120 unique combinations. And that is your answer. Now, another question you might ask just for fun is how many of those permutations have the substring CD in that order in them? Now, there's a couple ways to approach this problem, but the easiest, at least in my opinion, is that you just treat CD as a single string, as a single element. So in this case, you now have the elements A, B, C, D, and E as your possible elements, which means that now n is equal to 4, not 5. So again, using the same rule for permutations, we would say that this is just equal to 4 times 3 times 2 times 1, which is equal to 24. Now, if you want to go through and write out all those 120 permutations and show that only 24 of them have the substring CD, feel free. If you really want to prove it to yourself, you're all studying computer science or electrical engineering, write a Python program. Or if you're really feeling adventurous, write a program in C that would actually establish that there are only 24 permutations with the substring CD. Now, if we wanted to add another layer of complexity to this problem, we would say, well, how many permutations are there with either CD or DC? Well, at this point, because permutations are mutually exclusive, right? We've said that they're unique combinations. And in making CD a single element, we've eliminated all of the DC options. We can say that really, because we now have 2 potential elements to plug in, we really have this A, B, C, D, and E as an option, and then also A, B, D, C, and E as an option. So there's 2 different ways to enter this permutation that we calculated before as 24. So because there's 2 different ways, it's just 2 different stages. The first stage is select CD or DC. And then the second stage is find the number of permutations. So this would be equal to the number 2, the number of options in our first stage, multiplied by the number of permutations for a set with 4 elements, which is just 4 factorial. So in this case, we find that that number is equal to 48. Now, let's look at one last example here of permutations. And let's say that there are 6 people who need to sit at a round table. Let's make this slightly more interesting and insert the word round here with 6 chairs. And we'll say, how many unique orders are there? And just as a note, because it's a round table, everyone moving 1 seat to the left or right does not change the order of how they are seated at the table. So in this case, really what we've done is we've eliminated one of our choices. So previously, if this were not a round table and that moving left or right made a difference, we would say that the answer to this problem is just 6 factorial. But moving everyone left or right doesn't matter. And there are 6 different places that you could have a person start at. So we need to take this 6 factorial and divide by the 6 different places that each person could start at. Well, 6 factorial divided by 6 is just equal to 5 factorial, which is equal to 120 possible seating arrangements or unique seating arrangements for 6 people sitting at a round table where moving left or right does not matter. Now let's look at some examples of R permutations. Again, this is where you're only forming permutations of length R from a set of n elements. So first, let's say how many strings can be formed from the English alphabet where no 2 letters are the same. By definition of a permutation, you're picking unique elements every time. It's coming from a set with unique elements. So the no 2 letters are the same is kind of irrelevant information until we make it to repeated sampling later. In this case, the first question is, how many of those can be formed of length 5? Well, first, let's establish what our N and our R are in this specific problem. So because it's the English alphabet, N is equal to 26, the number of letters in the English alphabet. And R is equal to the number of elements that we are selecting from that set. In this case, it is 5. So R is equal to 5. And now that we have those 2 numbers identified, all we have to do is plug and chug into this formula, which is conveniently located on the slide. And we will find that the number of R permutations for a set N of length R is just equal to N factorial, so 26 factorial, divided by N minus R factorial. So that's going to be 26 minus 5, or 21 factorial. And if we plug those into a calculator and get the answer out, we'll find that this is 7,893,600 unique combinations of length 5. Now, if we wanted to ask that same question, but instead do it of length 7, well, N has not changed. We're still dealing with the English alphabet. There are 26 possible letters to select from. But now our R, the length of the permutations that we are making, has changed. It is now 7. So using the same handy-dandy formula from the corner of the slide, we can say that the number of permutations from a set of 26 elements that are of length 7 is going to be equal to N factorial, or 26 factorial. That part doesn't change. But what does change is this N minus R term here. And N minus R in this case is 26 minus 7, or 19 factorial. So as opposed to dividing by the 21 factorial above, we're now dividing by 19 factorial. And we'll find that that difference of 2 actually makes a pretty big difference, because now instead of 7 million possible permutations, there are now over 3 billion permutations, specifically 3,315,312,000 total permutations of length 7 from a set of 26 elements, in this case the English alphabet. Now for our next practical example, we're going to have a little bit of fun. We're going to use some Star Trek references. And the question we're trying to answer is, how many ways can 3 Vulcans and 5 Andorians stand in a line if no Vulcans can stand next to each other? So this is easiest to think about in 2 phases. And the first phase is really that the 5 Andorians stand in a line. And then the second phase is that the Vulcans have to fit kind of in between where those Andorians are, because they can't stand next to each other. They have to stand with an Andorian on at least one side of them if they're on an end of the line, or an Andorian on both sides of them to keep those Vulcans from standing next to each other. So let's say that our Vulcans are going to be represented by red and the Andorians by blue, and let's draw a picture. So the first thing that we'll say is that we have our 5 Andorians that have to stand in a line. So we have 1, 2, 3, 4, 5 possible places for our Andorians to stand in this line. And then the second phase is that the Vulcans have to fit in. And so after the Andorians have formed their line, the Vulcans can fit in 1, 2, 3, 4, 5, 6 possible places in this line. So the easiest way to look at this is, again, 2 different permutations. Now, the first permutation is pretty easy. 5 Andorians can stand wherever they want, so that is actually just a standard permutation. That is not an R permutation. So this is going to be 5 factorial for the number of ways that the Andorians can stand in a line. And 5 factorial, we determined earlier, is 120. Again, that's just 5 times 4 times 3 times 2 times 1. Now, for the Vulcans, it's going to be a little bit different. The Vulcans have 6 different places that they can stand in line. Again, that's anywhere that we have a red circle. But there are only 3 Vulcans. And so we can treat this like an R permutation. We can say that this is really a set of 6 possible elements, and we are selecting 3 of them for the Vulcans to stand in. And so in this case, this is an R permutation with N equal to the number of spots, which is 6, and R equal to the number of Vulcans, which is 3. So in this specific scenario, what we're left with is N factorial, or 6 factorial, divided by N minus R factorial, which is going to be 6 minus 3, or 3 factorial. And what we'll find is that this is equal to 720 divided by 6, which conveniently is also equal to 120. Because these were 2 successive stages, right? We placed all of the Andorians and then we placed all of the Vulcans. We go back to our basic counting principle saying that we just multiply these 2 numbers together, the 120 and the 120 from each of our phases. And so what we can find is that the total number of ways that 3 Vulcans and 5 Andorians can stand in a line, if no Vulcans are standing next to each other, is 120 times 120, which is equal to 14,400.